us now solve differential equation using methods of separable equation. So there are two steps on how to solve first order differential equation using the methods of separable equation. So the first one is separating the variables x from the variable y, and it's either through algebraic manipulation or through factoring first. And once we were able to separate the two functions to find the general solution of the differential equation, so we just need to integrate such two functions. So the two methods to be employed here would be one, the first step is to separate, and the second step would be to integrate. Okay, so to practice, okay, so such methods, so let's try to solve one differential equation. So for our example number one, so we have a differential equation x plus 1 dy minus y dx is equal to 0. Okay, so there are two terms here. So the first term involving dy and the second term involving dx. So our first step is to separate the two terms, and this can be done by transposing the y dx to the right side, so giving us an x plus 1 dy, and that will be equal to y dx. And from here we have dy on the left hand side and dx on the right hand side. So to again separate the two, so we could multiply both sides, so by or actually dividing both sides by y to separate y from dx, and x plus 1 to separate x plus 1 from dy, and this will yield to an equation so such that dy over y would be equal to dx over x plus 1. So from here, we were able to separate the equation so such that all y's are on the left hand side and all x are on the right hand side. And then from there, to find the general solution of the differential equation, so we will be integrating both sides. So the integral of dy over y then, so would be the natural logarithm, so such that this would be equivalent to ln y, and then that would be equal to the integral of dx over x plus 1. As you can see here, so our numerator would be equivalent to the denominator would be equal to x plus 1, and then deriving such denominator, so that would yield to dx. So as you can see here, the derivative of the denominator so will yield to the dx, which is our numerator. So in such case, so therefore the integral of dx over x plus 1 so would be equal to ln of x plus 1, and of course plus our constant c. And then to simplify our general solution, so we will be employing the properties of logarithm, so such that ln y, but before doing that, so ln x plus 1, so that is the same as, or this c, so which is an arbitrary constant, and then appending ln on our constant would still be a constant. ln c is still a constant c. So we are doing such case So for us to combine using the properties of logarithm. So ln y then is equal to the combination. So using the properties of logarithm, so if that would be an addition, so that would serve as a product of the x plus 1 multiplied it with c. And then from here, so since the left-hand side and the right-hand side involves a natural logarithm, so we could take the exponential function on both sides, so yielding to just simply y, and that would be equal to, I'm going to write c first, and then multiplied it with x plus 1. So giving us the general solution of the differential equation to be equal to y is equals to c multiplied it with x plus 1. So that is for our first example. So let's proceed with another example. So in this case, we have another simple one, but this time, so it involves an initial value. So our problem or our differential equation is dy over dx, and that is equal to negative x all over y. However, this is an initial value problem, so since the initial value is given that when x is equals to 4, so y is equals to negative 3. So to resolve such problem, so this one is direct to the point that dy over dx is equals to negative x all over y, and then multiplying both sides. So we want to transfer dx to the right side, so therefore I am multiplying the equation by dx, and at the same time I want y to be transferred to the right side, so therefore I'm going to multiply y as well. So giving us y dy, and that would be equal to negative x dx. So as you can see on the separated equation, so this one is integrable right away. So the integral of y dy, so using power formula, so giving us y squared all over 2, and that would be equal to negative x squared all over 2, and that would be plus c. And then if we want to simplify the expression of our general solution, so we will be multiplying everything by 2, so giving us y squared is equals to negative x squared, and then plus 2 multiplied with a constant c, that would still be a constant c, so giving us plus c. And from here, it says that whenever x is equals to 4, so y is equals to negative 3. So the general solution of y squared is equals to negative x squared plus c can be transformed into its equivalent particular solution, so by substituting the value of x as well as the value of y. So for us to determine our arbitrary constant c. So in such case, so y would be negative 3 squared and equals to negative, so x is 4 squared plus c. So giving us c to be equal to negative 3 squared, that is equivalent to 9, and then 4 squared would be 16. However, if I am going to transpose it to the right side, so giving us plus 16. So making c to be equivalent to 25. So therefore, we can now rewrite our general equation, or our particular equation, to be y squared is equals to negative x squared and then plus 25. Or we are writing this one to be equivalent to x squared plus y squared, which is equal to 25. So therefore, it appears that our particular solution would be an equation of a circle. X squared plus y squared is equals to 25. So next, let's have another example. So as you can see here, we are just solving differential equations, and from each example, so we are employing different methods of integration. So in a way, so this would be a review as well on the different methods of integration, so based from your Calculus 2 course. On the third example, so we are given a dy over dx, which is equals to y squared minus 4. And again, so looking at the differential equation, so this is a obvious separable equation. So in this case, I'll be employing some shortcuts so that our solution will be faster. So in this case, so we can right away rewrite our differential equations, and since this is a separable, so this one becomes dy over y squared minus 4, and that would be equal to dx. So the separated equation is dy over y squared minus 4, and that is equals to dx. So as you can see here, it's already separated. The only thing that matters now is how do we integrate such equation. So usually whenever the students are seeing y squared on the denominator, so usually it resembles the equation to be solved using inverse trigo. However, take note here that we have a negative 4. So therefore, inverse trigonometry or inverse trigo functions are not applicable in solving such equation. So in this case, the method on how to solve such equation is through partial fraction. So decomposition of a given function into its equivalent partial fraction. So in this case, I am going to separate first the 1 over y squared minus 4, and this one, or y squared minus 4, is factorable using the sum or the difference of squares, so yielding it to be y minus 2, then the other would be y plus 2. Okay, so the sum and difference, so it will yield to the difference of 2 squares. And using the partial fraction decomposition, so one of the factor 1 minus 2, and we're going to add, so y plus 2. So since the denominator is linear and non-repeating, so I could write variable a for the numerator and the other one to be equal to b. And our objective now is to determine, so what's the value of a and what is the value of b. So to find those values, so we will be multiplying the entire equation by y minus 2 multiplied with y plus 2. And as you can see here, so the denominator would cancel out, so leaving us 1. and then that would be equal to a. So y minus 2 and y minus 2 would cancel out, so giving us y plus 2. And then plus b, so y plus 2 would cancel out, so leaving us y minus 2. And then from here, so in order for us to determine, so what's the value of a and what's the value of b, so let's try to solve first. How do we get the value of a? So to do that, we will be assuming a certain value of y. So our objective here is to eliminate b. So to eliminate b, so we need a constant that will become 0. Okay? So once we multiply 0 with b, so that would cancel out. And that is when y is equals to 2, okay, 2 minus 2 is 0. So eliminating the value of b. So giving us that is 1 is equals to, then when y is 2, so 2 plus 2 is 4. So giving us a, multiply it with 4. And y is 2, 2 minus 2 is 0, eliminating the value of b. So giving us a to be equivalent to 1/4. And then when y becomes negative 2, so that would still be 1. However, this time, the negative 2 plus 2 is 0. And leaving us b to be equivalent to negative 2 minus 2, so which is negative 4. So giving us b to be equivalent to negative 1/4. So therefore, 1 over y squared minus 4 is the same as 1/4 over y minus 2, and then minus 1/4 over y plus 2. So that would be the partial decomposition of the original equation that we have. So in that case, so I could rewrite my original equation. So this time it becomes 1/4 over y minus 2 minus 1/4 over y plus 2. Then everything is multiplied with dy, and that would be equal to the x. And from here, so we can now integrate the given equation. So as you can see here, the one on the denominator is y minus 2, and its derivative, the derivative of y is dy, which is exactly the numerator of the given term. So therefore, the first term can be resolved using the natural logarithm. So similarly, that is the same method that we will be using on the second term, and the last term so would just be a simple power form. So therefore, giving us the integral to be 1/4, so ln of y minus 2, and then minus 1/4 ln of y plus 2 is equals to x plus c. Then multiplying everything by 4, so to simplify our equation, so giving us ln of y minus 2 minus ln of y plus 2 will be equal to 4x plus c. And combining, so combining our on the left hand side, so using the properties of logarithm, so giving us ln of y minus 2 over y plus 2 would be equal to 4x plus c. And taking the exponential function on both sides, so yielding to y minus 2 all over y plus 2, and that would be equal to This is the same as e raised to 4x multiplied it with e raised to c. And furthermore, so y minus 2 all over y plus 2 would be equal to e raised to c is still a constant. So rewriting this one, so giving us c e raised to 4x. So we could just leave it as is, or if you want to retransform it on another way, that would be fine. So, but for us, so this one will do already. So our general solution, so for our differential equation is y minus 2 all over y plus 2 is equals to c e raised to 4x. So now let's have another example, but this time, so it employs trigo functions. So example of which would be this one. And at the same time, it's an initial value problem. So e raised to 2y minus y cosine x dy over dx is equals to e raised to y sine 2x. And then when y, or when x is 0, y is 0 as well. So to separate such functions, so let's just try to look at the differential equation. So the one on the left hand side, so e2y minus y is a y function multiplied with dy. So cosine x and dx are the one on the left hand side. Ey is the one on the right hand side. But if we want to transform this one wherein every or all of y's are on the left hand side, so let's try to do it on this way. So such that e raised to 2y minus y all over e raised to y multiply it with dy, so would be equal to, so in everything on the right hand side, so we'll have sine 2x. So since dx is on the denominator, so once we transfer it to the right hand side, so it would become a multiplication, so sine dx, and then divide it with cosine x. So as you can see here, we were now able to separate every y on the left hand side and all x are on the right hand side. So our problem now is to integrate. Okay, so on the left hand side, so there is an operation that is involved, so which is a division. So in such case, so usually before we integrate, so we perform the operations involved. So in this case, so this would be the same as e raised to 2y all over e raised to y minus y all over e raised to y, and everything is multiplied by dy. And the one on the right hand side, we cannot right away integrate. Okay, so we cannot right away integrate such functions, but we can use some identities, so that would help us in simplifying the given function, so for us to integrate it in such a way that sine 2x is the same as, or a double angle, so that would be the same as 2 sine x cosine x, and then dividing it with cosine x dx. And as you can see here, so we can cancel out cosine x and cosine x. So leaving us the one e raised to 2y divided with e raised to y, so that will just be e raised to y. Then minus y, so I could transform ey, so going to the numerator, so making it e raised to negative y, and everything is multiplied by dy. And then the one on the right hand side, so it's just a simple sine function, so 2 sine x dx. So from here, it is more simplified, and we can now integrate such equation. So the first term ey is just the method for exponential function, 2 sine x is a direct trigo function, integral for sine. But here, so we have a negative y e raised to negative y. So this involves a special method. So we can solve this one using integration by parts, but easier one. So since it involves a product of any function to an algebraic function, so the easiest way would be through tabular method. So through tabular method, so we could write negative y here, and then we could have a negative ey dy on the right hand side. So the tabular method again, so we are differentiating the algebraic function and then while integrating the other function. In this case, the derivative of negative y is negative 1, and then negative 1 is 0. So we usually stop whenever our derivatives becomes 0. And then the integral of negative or e raised to negative y would be e raised to negative y, and then derivative of negative y is negative dy. So we need a neutralizing factor of negative 1, so giving us the integral to be negative e raised to negative y. And similarly, the integral of e or negative e negative y would be equal to e negative y. And then, so using our signs, so the first one should be positive, and then the second one would be negative. So from here, so we can write our equation to be equivalent to e raised to y, and then, so using our tabular method, so the integral of negative y e raised to negative y, so would be negative y times negative y. So we'll have plus y e raised to negative y. Then negative and negative, so giving us plus e raised to negative y, and that would be equal to the integral of 2 sine x would be equivalent to negative 2 cosine x, and that would be plus c. And since the given problem is an initial value problem, and it says that when x is equal to 0, so y is equal to 0 as well. So substituting those initial values, so will give us the value of our arbitrary constant c. So giving us e raised to 0 plus 0 multiplied with e raised to negative 0 plus e raised to negative 0 to be equal to negative 2 cosine 0 plus c. So e raised to 0 is 1, and then anything multiplied with 0 is 0, plus e raised to negative 0 is as well 1, and that is equal to negative 2 cosine 0 is 1, so plus c. So giving us the value of c to be 1 plus 1 is 2 plus 2, which is equal to 4. So giving us the particular solution to be e raised to y plus y e raised to negative y plus e raised to negative y is equals to negative 2 cosine x plus 4. So that would be our particular solution. But if we want to express this one explicitly as y, and that would be difficult. Okay, so I'll just leave it on this way. So therefore, our particular solution so would be e raised to y plus y e raised to negative y plus e raised to negative y is equals to negative 2 cosine x plus 4. Okay, so that is for our example number 4. So let us now proceed with our last example. So on this last example, this is not the typical method that we will be using for separable equation, because looking at the given differential equation, so as you can see here, the variables x and y are separated by an algebraic operations of plus and minus, so which is difficult in separating the variables x and y. However, the other method that we will be employing, so in separating the values of x and y, so would be to use method of factoring first. And to factor this out, so in particular, so we can use factoring by grouping. So as you can see on the given differential equation, so the first two terms, so there's something that is common on the first two terms on the numerator, so similarly on the denominator as well. So rewriting the given equation, so that would yield us to dy over dx, and that is equal to the first two terms. So what is common here is x. So that is x multiplied it with, so xy divided with x, so that would give us y, and 3x divided with x, so that would give us a plus 3. And as you can see here, we have a y plus 3, but the one on the remaining one is negative y minus 3. So in here, I can factor out a negative 1. So negative y divided with negative 1 would be positive y. Negative 3 divided with negative 1, that would be positive 3. So as you can see here, so y plus 3 is common again on the numerator. But how about on the denominator? On the denominator, so x on the first two terms is common as well. So that would give us x multiplied with y minus 2. And then on the second term, or on the second two terms, so we have 4y minus 8. So what is common on both would be a positive 2. So 4y divided with 2, or sorry, that would be 4. So 4y divided with 4, so that will be y. Negative 8 divided with positive 4 will have a negative 2. So again, at this point, we could still not separate the variable x and y. So we can further factor this out. So using for the methods of grouping, so you can see we only have two terms, the first term and the second term. And what is common on both terms would be y plus 3. So this term divided with y plus 3, so leaving us an x, and negative y plus 3 dividing it with y plus 3, so leaving us a negative 1. Divided with, on the denominator, so what is common again on both terms would be y minus 2. So x times y minus 2 divided with y minus 2 gives us an x. And then for y minus 2 divided with y minus 2, so leaving us a positive 4. So therefore, this time we have a differential equation on the separable equation format. As you can see here, so we have y plus 3 all over y minus 2 as our function of y, and then the x minus 1 over x plus 4 as the function of x. So using the separable equation, so we can separate y from x, and our y minus 2 will become our numerator divided with y plus 3, and that is multiplied with dy, and that would be equal to, so we're retaining the x minus 1 all over x plus 4, and then transposing dx, so giving us x minus 1 all over x plus 4, multiplied it with dx. And now, so we will integrate both sides. So since we were able to separate y from x, so how do we integrate? So we cannot use right away natural logarithm, because if we're going to derive y plus 3 So that would be dy, but on our case, we have y minus 2 on the numerator. That's the same case on the right-hand side of the equation. So since this is an improper fraction, so as I've mentioned before, if we can perform the operation first, then perform the operation first. So in this case, we can divide the numerator by the denominator so as to integrate such equation. But to prevent us from doing the long division, so what I would be suggesting is that if I would have y plus 3 on the denominator, so I could write y plus 3 on the numerator as well. Okay? But the problem is, the one on the numerator there is negative 2. So since I added plus 3 here, so therefore, I need to subtract 5 on the numerator. So such that if we have positive 3 minus 5, so that would give us still a negative 2 without changing our function for y. So similarly, that's the one that we will be doing on the right-hand side. So if we have x plus 4 on the denominator, we should have an x plus 4 on the numerator as well. But what we have there is a minus 1. So we have plus 4 here. So to give us a minus 1, so we should have a minus 5 on the denominator or on the numerator. So 4 minus 5 would be negative 1. So which is the same as the one above. Okay. So giving us, so we could separate this time as y plus 3 all over y plus 3. And minus 5 all over y plus 3. Then everything is multiplied with dy. And again, that would be equal to x plus 4 over x plus 4 minus 5 over x plus 4 multiplied it with dx. And to simplify this one further, so we can rewrite this to be equivalent to 1 minus 5 all over y plus 3 dy, and that is equal to 1 minus 5 all over x plus 4 dx. So this time we can now integrate both sides. So to integrate both sides, so 1 times dy is just dy, so the integral of dy would be y. And since our denominator is only y plus 3, its derivative is dy, so which is our numerator. So therefore, this would be equivalent to negative 5 ln of y plus 3. And that would be equal to the integral of 1 dx would be x, then minus 5 ln of x plus 4. And then that would be plus c. And then transposing so that we could combine the two natural logarithm function. So giving us 5 ln of x plus 4, then minus 5 ln of y plus 3. So that would be equal to x minus y plus c. So to combine the two natural logarithm function, so we could have ln of x plus 4 raised to 5 minus ln of y plus 3. So using properties of logarithm, so that's the same. So it would be x minus y plus c. So combining the two, so that would give us ln of x plus 4 over y plus 3, then that would be raised to 5 is equals to x minus y plus c. And taking the exponential functions of both sides, so giving us the final answer to be x plus 4 over y plus 3. Then that would be raised to 5, and that is equals to c e raised to x minus y. So giving us our final general solution. So to be equivalent to x plus 4 over y plus 3 raised to 5 is equals to c e raised to x minus y. Okay, so that's it. So that's are all the examples. So for separable equation.